All right, so I'm going to go through the homework review. It's located in week 11 module. The first thing I just want to look at is look at question number 2. Question number 2 looks like this. Is it okay if I change the S's to X's because my S's look like 5s? There we go. So this is question number 2 in the test 3 homework review. And we want to find the derivative of this. So, I mean, I just want to just reintroduce derivatives. Everybody should be able to take the derivative of all these. Some of them are time consuming, but let's just take a look at it. To take the derivative of this, you have to rewrite it. It's very similar to taking the derivative of a function like this, 2 over x. The way we did this one was we just brought the x up to the top and gave it a negative power and then took the derivative. So that's what we're going to do here. We're going to bring the x minus 3 to the top and give it a negative 1 power. It brings it to the top. So now we should be able to take the derivative, and negative goes in front. And oh, by the way, let me start this again. You can use a chain rule, but if you recognize the chain rule, so if you want to, you can actually recognize that this is the chain. I think it's easier recognizing that it's the chain rule. So h prime equals 2. This is not h prime yet. This is 2u to the negative 1. If u equals x minus 3, so u prime just equals x. It doesn't equal x, it equals 1. So if you recognize it equals 1, you could just do it the other way. But I mean, normally if you're busy with stuff down here, if there was a 2x squared or something, you'd use the chain rule. So I'm just going to use the chain rule. So when I take the derivative of this, the negative comes in front. And I get negative 2u, and then you subtract 1. Negative 1 and negative 1 is negative 2, and then you get u prime. So that's the chain rule. And then when we plug everything into, u was x minus 3 to the negative 2 power, and u prime was 1. You see that u prime really doesn't change anything. The 2 times 1 is still 2. This is the answer, which also can be written with 2 on top and x minus 3 squared on the, oh, there's a negative here. So it could be written either way. So I just wanted to show that, taking the derivative of that. Just want to make sure everybody has all these derivatives down. I've gotten a few questions from people in the last couple of weeks on taking a couple of derivatives. Probably about 3 or 4 different people have talked to me about certain derivatives. So I just want to make sure we have that. All right. So let me go look for the next one I want to do. Should have wrote these down first. I do want to do number 4. Once again, we're doing test 3 review, the homework review. Number 4 says the height of an object is this function, negative 4.9 t squared plus 430. The height of an object after dropping in t seconds after dropping from a height of this, right? This is the position function, also known as the height function. And it says find the average velocity of the object during the first 5 seconds. So find the average velocity. during the first 5 seconds. Velocity is distance divided by time. So we want to find the average velocity starting off when time equals 0 and then time equals 5. So I mean, in other words, here, this is time and this is distance, an x and a y, a t and a d or s or whatever you want to call it. So I want to find the distance at 0, and then I want to find the distance at 5, from starting at 0 seconds to 5 seconds. If I put 0 in the original function, I get negative 4.9, 0 squared plus 430, I get 430. If I put 5 into the original function, negative 4.9 times 5 squared plus 430, I'm going to put it in my calculator, figure out what I get. Negative 4.9 parentheses 5 squared plus 430, and I get, when I put 5 in there, I get 307.50. Okay, so find the average velocity. Find the average velocity is the change in distance divided by the change in time. In other words, y2 minus y1 divided by the time 2 minus time of 1. Y, let's call this the first point and this the second point. So y2, this is y2, this is x1, or x2, sorry. This is x1 and this is y1. So y2 is, let me put it down here, y2 is 307.5, y1 is 430 divided by y2 minus y1, 5 seconds and 0 seconds. So 307.5 minus 430, hit enter and divide that by 5. I get negative 24.5 meters per second. We're using the unit. So that's the velocity. That's the average velocity, negative 24.5 seconds. So then it says, so that's, I mean, that's one of the answers, negative 24.5 seconds. So let me erase this now. That's my average velocity. And if you remember, pretty much we use the two endpoints, the 0 and 5, to find our average slope, or find our slope. That's what we just did. This is the distance formula, and velocity is the derivative of this, or you could also say velocity is distance divided by time. In algebra, we didn't, we don't take the derivative when we find that. We just did change of y divided by change of x. And we got, so our average velocity was negative 24.5. In other words, whatever this thing was, wait, The height of an object after it's dropped is 430 meters per second. All right. Find the average velocity of the object. Yeah, the average velocity was negative 24.5 meters per second, and it's negative because it's falling down. And then part B says use the mean value theorem. Remember, I'm just going to draw. This is a rough. This is the function is a negative x squared, a negative t squared. So it's a parabola, inverted parabola, and this is an inverted parabola, and we picked a point from zero, and I'm not quite sure. Let's call it here from 0 to 5 seconds. So if we're looking at the inverted parabola, we're only maybe looking at this part from, if it was on the x-axis. I don't know where the x-axis is. We'll call this from 0 to 5. So we're just looking at this point. We're looking at this part. We're looking at this part. So we just found this, the average velocity. Oh, by the way, I drew that wrong. Since it's negative, it should be. Maybe we're looking at this part from here to here. So because it's a negative. There we go. Negative slope. That's 0, and we're going to call this x-axis 5. Says use the mean value theorem to verify at some time during the first 5 seconds of fall the instantaneous velocity or average velocity. So if this average velocity was negative 24.5, it's saying the mean value theorem says someplace on my graph that we have the same slope. Do you see? I'm not sure exactly where. I'm going to say about right there. Somewhere on my graph, we have the same line, the same slope as this one, that this slope also equals negative 24.5. In other words, the first derivative equals negative 24.5. So average velocity and a point on the between those 2 points have the same slope. So we have to take the derivative of s, because the derivative of s is the same thing as taking the velocity, right? Derivative of a distance is velocity. And if I bring the 2 in front, negative 4.9 times 2 is negative 9.8 t. Subtract 1 to the 2, and you get 1. And then derivative of 430 is 0. So this is the velocity function. Negative 9.8 t. And we want to know what t is. At what time, where, what is the time that this equals the same slope? Well, in order for it to be the same slope, you have to say the velocity is the same. So this velocity is the same as our average, negative, I'm going to erase this right side now so I don't get too far down. Velocity equals negative 9.8 t, 24.5 equals negative 9.8 t. Do you see? We want to know where the velocity is the same as the average velocity. So we just change our derivative. The velocity is negative 24.5. We divide both sides by 9.8. And we get negative 24.5 divided by negative 9.8. And the time is 2.5 seconds later. So if we had 2 points and we found the average velocity, there's a point on the graph where the velocity is the same. They're both negative 24.5. This was at 5, this time 5, this was at time 0. This point, if I drew it correctly, was at time 2.5. So the answer is at time 2.5. That's where my instantaneous velocity is the same as my absolute velocity. Everybody okay with that? So there definitely will be an average, find the average, and then find the instantaneous. All right, moving on. Does anybody have any particular one in that sheet to do? Did anybody have any particular one they wanted me to do? See, number 5 is very similar to number 4. Kinda. Number 5 deals with Grohl's theorem. It showed that 2 points are equal, so that means there should be a first derivative that equals 0 somewhere in there. I mean, really similar to what I did. Mean value theorem and Rolle's theorem, these both look really similar. 6 is mean value theorem. Nobody wants any particular one done. Let's see. Use a graph to estimate the open intervals in which the function is increasing or decreasing. It says use the graph. I'm going to do number 7, but I'm going to change it a little bit. So I'm going to do number 7. Number 7 looks like this: y equals negative x plus 3 squared. Now it says use the graph to estimate the open intervals. What if they didn't have a graph? so they have a graph here. They have a graph. And I don't want to use the graph. Let's say there's no graph in the problem that you're going to get. And we want to know where the function's increasing or decreasing. We want to know where the function is increasing or decreasing. So it says, so let's say the question is this: indicate the interval function is increasing or decreasing. So the way to do that is first take the first derivative. We want to find a critical number. The critical number, right? And this is a negative x squared graph. X squared. So this is a negative x squared graph. You have to understand the shape of this graph. This is an x squared graph, but a negative in front of the x squared, it looks like this. So the first thing we should do is find this point. That's the critical point on the graph. And you find that the critical point, that's where our slope equals 0. That's where our first derivative equals 0. So let's take the first derivative of this function. And once again, you notice if there's just an x, that means u is 1, and you don't have to use a chain rule, but I'm still going to do it. This is a negative u squared, where u equals x plus 3. So the derivative of u is just 1. The derivative of x is just 1. So the derivative of this is, by the way, that's not the derivative yet. Now it's the derivative. Bring the 2 in front, u, and then subtract 1, which is just 1, and then u prime. So negative 2u, u is x plus 3. And then u prime is just 1. So the first derivative is negative 2x plus 3. And we're finding the critical number. I know I found the derivative, but now I'm trying to find a critical number. To find a critical number, you have to set the derivative equal to 0, right? That's right here. You have to set the slope equal to 0 to find that point. When you divide both sides by negative 2, nothing happens. You get x plus 3 equals 0. Bring the 3 to the other side, and you subtract 3 to both sides, and you get x equals negative 3. So our graph looks something like this, and the x value of this point is negative 3. On a graph, our x value is negative 3. So our interval, so I'm going to erase some of this now because we're trying to find out where the interval is increasing, decreasing. You can actually break out your calculator and look at it right now, but I want to show you we have to do our interval. If our critical number is negative 3, our interval is from negative infinity to negative 3. The second interval would be from negative 3 to infinity. You see you have one critical number at negative 3. That's a critical. Do a test point over here. Test point, I'm going to put negative 4. And I'm going to do a test point over here. I'm going to do a test point of 0. If I put negative 4 in the derivative, oh, what did I get? There's a derivative. Did I do something wrong? Wait. Seems like I think it looks like the book is wrong. I mean, it said you bring that over and subtract 1. Oh, I think they thought that was supposed to be a negative. So, by the way, the answer key for this problem is wrong. I'm glad I'm doing it. The answer key for this problem is wrong. So I am glad I'm doing this problem. The answer key shows a different derivative, but they're thinking that the 2 has a negative on it. And the original problem doesn't have it. Let me go back up to the original problem. Let's see. The original problem doesn't have a negative power. So no, the power does not have a negative. If they did it and they solved it as though the power was negative. So the way the book did this problem is wrong. By the way, my derivative, once again, I'm going to put my derivative here. My derivative, we brought the negative 2 in front, and then it was x plus 3, right? That was the derivative. That was the derivative. Brought the negative 2, subtract 1, yes. So we put a negative 4 into the test point, and I get negative 2, negative 4 plus 3 is negative 1, and I get a positive 2. And it doesn't matter what number I get other than I know it's positive. That means it's an increasing function. So you have to understand that first derivative rule, that critical number. When you put a test point in there, if it's positive, you know the graph is going up. You see, it's an increasing function from negative infinity to negative 3. So now I'm going to put 0 into the function. So if I rewrite the function negative 2 times 0 plus 3, I get negative 2 times 3, which is negative 6. It's a negative number. That means negative slope, negative first derivative, means it's a decreasing function. So from negative infinity to negative 3, this function is increasing. It's a positive. Increasing means a positive slope. And then from negative 3 to infinity, we get a negative slope. That means it's a decreasing function. And you can look at it just from the picture. Increasing, that's a positive slope, and it's decreasing from negative 3 to infinity, the other one. All right, I'm glad I did that one because the answer key is wrong. Hope that doesn't confuse anybody.
Mr. Chapman,
Yes.
just real quick, you said that they mistakenly did the quotient rule when they
No,
got the derivative. Is that what they did?
no, they thought. Do you see the? Let me erase this and I'll show you.
Because I think their starting point from my interpretation is they started off with -2 x plus 3, and they thought they had to do the quotient rule to get the derivative.
No, well, this is the original function, right?
Yeah,
And this is the answer they got.
yeah, 2 over, yeah.
Okay, I'm going to tell you why they got
Two.
that. Because they meant to type this in. Do you see? You
Yes.
bring, I think they meant to type that in, and when you subtract 1, you get the 3.
Yeah, I
So
see.
I think they made a mistake typing the
Okay.
original problem in. So if this was the problem, what we did was correct.
Okay.
Okay, it looks like they meant to put a -2, and they still had the sign wrong on the derivative. Oh, actually they didn't, because you put the, yes, because if it was a -2, negative and a negative change to a positive. So this is definitely wrong in the answer. So
Yeah, I
read.
think I emailed you, I think, before, because I was watching one of their demonstrations, and I think they also made a mistake like that where they forgot a negative sign, and
Right.
I was like,
Okay.
I lost like an hour or something just trying to see how they got it. And I was like, oh,
Uh,
they forgot a negative.
yeah, consider that a learning experience. I don't know how many hours I have wasted on bad problems. But yes, that happens. And
Thank you.
I'm looking at that. I'm really surprised nobody picked that up, because I used the same thing last semester. So unless somebody did mention it to me and I just ignored them, that could have happened. Hopefully not, but that could be. Okay, let me get back to where I was. I'm on my other computer also looking at this together. Identify something increasing and decreasing. So number 8 is finding where it's increasing and decreasing. Same thing. Take the first derivative, find the critical numbers, then take the test points. Consider the following function. Find the critical number here again. Find the open intervals where it's increasing and decreasing. See, I like these because they're really simple derivatives and everything. And you set the 0. So those shouldn't be too hard. Let's do number 10, because number 10 is not difficult as far as calculus goes, but there's some algebra you might want to take a look at. So you have to be familiar with the algebra part. So I'm going to look at number 10. Number 10 is this function. 3x to the third plus 9x squared minus 27x. And first it says find the critical numbers and then increasing and decreasing. So we're going to find the critical number first, find out where the first derivative equals 0, right? So once again, the critical is where the first derivative equals 0. Critical numbers are the peaks and valleys. I got to keep on re-saying that. I get quite a few people to ask me, that over and over. It's okay. You just have to say it to yourself over and over again. Critical numbers are the peaks and the valleys. It's where the slope equals 0, the highest point on a graph or the lowest point on a graph, as far as relative minimums or relative maximums. All those words are the same: peak, valley, relative min, relative max, highest point, lowest point. So take the derivative of this, and you get 9x squared plus 18x minus 27. So that's the derivative. To find a critical number, the first derivative has to equal 0. And now we have to solve for x. Well, first thing I notice, all 3 terms has the factor of 9 in it, so I'm going to factor out 9. And I'm left with x squared plus 2x minus 3 equals 0. Okay, so I factored out a 9. And if you divide both sides by 9, right? If you divide both sides by 9, what happens is 0 divided by 9 is still 0. You just get x squared plus 2x minus 3 equals 0. If you divide both sides by 9, the 9 just disappears. And now we have to find x, so you have to factor this thing. And so you got to remember how to factor 3 and 1. The 3 has to be positive and the 1 has to be negative because you got to get a plus 2 here. We're not using the AC rule. We're using the simple factoring when the number in front of x squared equals 1. So x plus 3 equals 0, or x minus 1 equals 0, and you have to solve for x for both of these. When you get the number to the other side, x equals negative 3 or x equals a positive 1. These are the critical numbers. When you look at a graph, here's 0, here's 1, here's negative 3. These are our critical numbers. So we need to do each one of these intervals. We need to do the interval from negative infinity to negative 3. Then the next interval is from negative 3 to 1. And then the next interval is from 1 to infinity. So we want to find out where this graph is increasing or decreasing. We use the critical numbers to find those points and then the intervals between those. And don't forget, if it was a rational function, you also use the asymptote. So if there was an asymptote of 4, you have to plug that in here. You know, if there was an asymptote of 4, then there'd be another interval. So you just got to remember the critical numbers separate, and also asymptotes if you have any. This is not a rational function, so we don't have any. So then we do test points. I'm going to do a test point of negative 4, a test point here of just 0, and a test point here of 2. And I'm going to plug it into the first derivative. So if I plug negative 4 in the first derivative, I don't care what I get. I just want to know if it's positive or negative. But I'm going to do the whole thing. 9 parentheses, negative 4 squared plus 18 parentheses, negative 4. I'm multiplying 18 times negative 4 and then subtracting 27. And when I get this, I get positive 45. I get a positive number. Once again, I don't care what I get, as long as it's positive or negative. When I plug 0 into this function, that's an easy one. I get negative 27. I get a negative number. And then when I plug 2 into that function, 9 parentheses 2 squared plus 18 times 2 minus 27, I get a positive 45, and I get a positive number. So from negative infinity to negative 3, I get a positive first derivative. Positive first derivative means it's an increasing function. A negative first derivative means it's decreasing at this point. And then a positive first derivative, it's increasing at this point. So let's put that in our calculator and take a look at it. And when I say put it in our calculator, I'm talking about the original function. We want to graph the original function, not the first derivative. We want to graph that original function. See if I can plug my camera into it. There we go. So the original function y equals 3x to the third plus 9x squared minus 27x. And my window is set up. I think I need to increase my y value.
negative 25 to 25. Let's see if that helped. Close, a little bit more. Maximum, let's put 50 graph. God, how high does this thing go? Maximum window, 100. Okay, so let me, if you double click on my picture, I think you'll be able to see my calculator once I put it up there. So that's the picture I got, but this is the window. I mean, I had to change my window. I had negative 10, 10 for my X values. My Y values, I went negative 25 to 100, just so I can get the full picture into my window. So when I graph this thing, this is what I get. If you see from negative infinity to 3, from the graph all the way from negative infinity to negative 3, 1, 2, 3. That's right. That's a critical number. This is a critical number, and that is a critical number. Negative 3 and 1 are the critical numbers. From negative infinity to negative 3, the graph from left to right is going up. It's increasing. Then from negative 3 to 1, do you see the graph is decreasing? And then from 1 to infinity, the graph is increasing from left to right. So everything we just wrote down matches with the actual graph of on the calculator. So the calculator is a great place to verify, just to verify everything. I really wish I was making you show my work. Don't worry, if you take college algebra, calculus 2 in the fall with me, you're going to have to show. It doesn't matter who you're going to have. You're going to have to show work. All right, so that was that one. Let's move on. That was number 10. Let's see what else we have. Let's take the derivative of this next function. The reason why I'm doing this, just in case it's multiple choice and you have to take the derivative of this next function. Okay, so I'm on question 11. I'm really concerned about everybody taking derivatives. At this point, by the way, we're done with after test 3, we are done with calculus 1. Test 3 is the end of calculus 1. Test 4 is all about calculus 2 material. Starting next week, we're going to learn about calculus 2 stuff. In fact, when you take calculus 2, the very first week of class is the stuff that we're going to learn next week. My test 4 is the beginning, is like half of test 1 in calculus 2. So we're going to be learning the calculus 2 stuff starting next week, I think. Number 11, it gives us a function that looks like this. Minus the ln of x. And we want to take the derivative of this. I just want to take the derivative of this. So the derivative of this, first we look at this derivative. We bring the 15 in front and subtract 1. 15 minus 1 is 14. And it's over 15. So that's the derivative of that. The derivative of ln x. Ooh, I don't know about that. Anybody know what that derivative is? Anybody know?
Isn't it 1 over x?
Yes. If you don't know, for those of you who don't know, break out your formula sheet. The derivative of ln x is 1 over x. Okay? So I'm going to give you a couple of scenarios. I mean, this could be a really good multiple choice question. So 15x4 minus 1 over 15x is one answer. 15x, let's just put x4 minus 1 over x as another answer. That's 14, sorry. What else could we possibly have? Let's get crazy. X to the 15th minus 1 over x is another answer. Let's do, oh, you have to subtract 1 though. Let's try another one, x 15 over 15x. A, B, C, D, E, none of the above. You have to pick the correct answer. So you have to know, that's why I picked this problem. There's a little algebra involved. It's not a lot, but there's a little algebra involved here. So anybody want to take a guess? A, B, C, D, or E? Oh, never mind. How many people are actually looking at the how many people are actually looking at the answer key? So the answer is C. I forgot, you guys. I'm looking at the answer key on my other computer. I don't know if you guys are or not. But the answer key is C. So you have to do the math to try to make it look like C. You know, this answer is not on there. The way you make them look the same is you get a common denominator. So if my common denominator will be 15x. So for me to get 15 here, I have to multiply the top and bottom by 15, and I got 15x on the bottom. To get x over here, I have to multiply this by x and x, right? So now I have 15x on the bottom. And I have one fraction, so I have 15x. On top, x14 times x to the 1 is 15x to the 15. And then here we have 15 times 1, which is 15. The top, you can factor out a 15. And these cancel. So we get x15 minus 1 over x, which is C. So I just want to make sure you're able to use the algebra and manipulate the equation to look at one of the answers. Just because you're doing all the math correctly doesn't necessarily mean, what happened? Did I just delete let me stop. Oh, there it is. Just because you get the correct answer doesn't mean you can always pick the correct answer. You have to make it look like, I don't know what happened. Where is my, I thought I had stopped sharing. Did I delete? I think I deleted the file. Let me bring it back. Alrighty, so it's back. So let me start sharing it again. And we are back. Now it looks smaller. Give me another second. Oh, there it is, the plus, plus, plus. One more time. Yeah, there it is. Except I didn't want that. That's funny. I wanted the whiteboard. I am so confused with the Zoom. Sometimes the Zoom really kicks my butt. All right, so that was that one. Let's go. Let me look on here. What's next? Oh, damn it. I just found the derivative of that. Let me write down that derivative again because I want to answer the rest of the questions on there. It was the derivative ended up being x15 minus 1 over x. And the rest of the questions were, where is the function increasing, decreasing? And then finally, it says, where is the relative maximum or minimum? I think that's what it says. Where is the relative? Yeah. It said, apply the first derivative test, identify the relation relative extrema. Is it a relative maximum or minimum? So first we got to find a critical number. So remember, first derivative has to equal 0. That's a critical number. If I multiply both sides by this x, x times 0, nothing changes. Get the 1 to the other side, x to the 15 equals 1. Take the 15th root of both sides. And x equals the 15th root of 1 is 1. That's a critical number, 1. So we have from negative infinity to 1. And then we have from 1 to infinity. These are intervals. Pick a test point. Pick a test point. Here, I'm going to pick a test point of 0. I always like 0 if I can get it. Pick a test point of 2 here. And I plug this into the first derivative. Oh, I can't. By the way, that brings up a really good point. The critical number, we already said the critical number was 1. So, that we're okay there. I was going to say there's no asymptote here because this is not the original function. This is the derivative. So I was going to just say we have an asymptote. No, we don't. The original function, it was x15 over 15 minus ln x. There was no asymptote. There was nothing on the bottom of the original function to make an asymptote. So if I plug 0 in here, I don't like that when you plug it into the original function. So I'm going to plug, that's a bad test point. That's actually a bad test point. So I'm going to pick a different test point. Anything else will work. Let's pick -1. If I plug -1, I don't like that either. Oh, no, we can pick -1. If I plug -1 into the original function, it's -1 to the -1 to the 15th power minus 1 over -1. -1 to the 15th power is -1. -1 minus 1 is a -2. -2, hang on. Something is not right. Oh! 0. I knew that was, I got the wrong intervals. I apologize. Because we do have that 0. I recognize the 0, but it wasn't on the original function, but it is on the derivative. So that's really important. We can't pick 0. We can't pick 0, and that's why. Let me write down the original function again. This is the original function, minus ln x. Can somebody tell me the domain of this function? This is the original function. Anybody know the domain?
Is this where we look at the numerator?
Well, no, look at ln x. There, you have to understand.
The domain of the natural log is from I think you can't have one that's negative. Is that right?
Right. Try to, on your calculator, try to take the natural log of -1. Your calculator says error. You can't take the you can't take the ln of a negative number. Try the ln of 0. ln of 0. Do you see it also says error? So the domain of ln, x has to be greater than 0. It can't equal 0. X has to be greater than 0. Here the domain is x can equal anything. So the total domain of this function, you know, the domain of ln, that's the original function. The domain is from 0 to infinity. So the domain was from 0 to infinity. We found the critical number at x equals 1. We found the critical number at x equals 1. However, when we took the first derivative, I said asymptote has to be from the original problem. But if the first derivative has a x on the bottom of it, you also call that, it's not an asymptote in the original function, but it's considered, remember, if you remember, it said critical numbers or numbers that make the function undefined, not the function. Critical numbers or the numbers that make the first derivative undefined was so x equals 0 also makes the first derivative undefined. So we're using, when we do our intervals, we do all critical numbers and all numbers that make the derivative undefined. So we have to use these as our critical numbers. In other words, we start at 0, we go to 1, and then we go on the other side of 1 to infinity. This is our interval that we're looking at. That's why 0 didn't work. It's undefined. So that's the interval. We're not using negative infinity because no negative number will plug into natural log, into the original function. So this is the interval, and we're going to do test points in this interval. Test point of 1/2, and a test point here we can use of 2. If I put 1/2 in that function, in the first derivative, I'm going to try it. 1/2 raised to the 15th power, raised to the 15th power, arrow down, -1. And then I'm going to divide it by 1/2. I get a negative number. That means the function is decreasing. And when I put 2 into that function, 2 raised to the 15th power, then I -1, and I divide it by 2. I get some huge number. It's positive though. So it's an increasing function. So from 0 to 1, it's decreasing, and from 1 to infinity, it's increasing. That's a good one too, because I don't know, I'm picking all the good ones, because the domain there doesn't let you go from negative infinity to positive infinity. It only lets you go from 0 to infinity, not including 0, because the ln of 0 also is an error. The only way you can take an ln is it has to be a positive number, something greater than 0. Oh, but we're not done. So then it says, is this a relative minimum or maximum? So, I mean, look, our function, let's go to a number line. Here's 0, here's 1, here's infinity. It says from 0 to 1, the function is decreasing. It's from 0 to 1, and you can draw any decreasing function. There we go. The function is decreasing. Then from 1 to infinity, the function's increasing. The question is, at the critical number, at 1, what is that, a relative minimum or maximum? Well, if it's decreasing and then it's increasing, you always have a relative minimum. You always have a relative, you see it's decreasing and then increasing. And that was one of the rules, I think, in 4.2. If you have a decreasing function and increasing function, it creates that critical number, or it creates that first derivative equal to 0 at a minimum. It's a value. So I just wanted to look at that.
Mr. Troutman, did we have to find a point in this particular question?
This point right here?
Yes.
It's right here. X is 1. And then if you want to know the Y value, you just plug
Then
1 back into the original equation.
Understood.
Okay.
Thank you.
The critical number is the X value, and then plug that back into the original. Yeah, some of the homework made you do that. Some of the homework made for this. Oh, yes.
Yeah.
And this problem they did. You're
Yeah,
right.
looking at it now. Yeah.
So yeah, this problem they did. We ended up with the X value of 1, and if you plug 1 into the original problem right here, 1 into the original problem, if you look at the ln of 1 equals 0. ln of 1 equals 0. So it's 1 over 15 minus 0. So the Y value is 1 over 15. So that is the minimum. It says find the relative minimum. This is the coordinate for the relative minimum.
Mr. Troutman, would it be would you be okay with if we could do number 13?
Okay, let's try that one.
It might take some time though.
No, I'm not happy about that.
The reason I asked
yes.
is
Let's look at those derivatives. Yes, quite a few people have asked about a problem similar to this. So yes, let's take a look at this. I'm going to show you. I might not go all the way through it, but
sure.
I'm going to show you how to get the first derivative and the second derivative.
Thank you.
Yes. And by the way, you're not the first. I've had quite a few people ask me about this. When I say quite a few, maybe 4 or 5. Well, maybe 4. But in the past, yeah, when I have larger classes of 30 people or so, everybody, yeah, this is one I usually do in class. So I'm glad you brought this up. So here's our function, 22 over x squared plus 12. So there's no x on top of this function. So, I mean, I've already done this derivative, this one twice. If you look at, I mean, the process of this derivative, finding the first derivative twice. So the first derivative, by the way, I'm not going to do the first derivative yet. I'm trying to erase this. There we go. What I want to do is rewrite this. I mean, as soon as I don't see an x on top, I'm going to rewrite this function to be this. And I can then rewrite it once again to be this, where u equals x squared plus 12. So for the first derivative, we're going to use the chain rule. X squared equals 12, and then the u prime equals 2x. Okay? So this is our function. And the derivative of this function, oh, wait. Everybody agree there should be a -1 there? When I brought it to the top, there should be a -1 there.
Yes.
Okay, thanks. So the derivative of this function, you bring the negative in front, and then you subtract 1. And then you have u prime. So f prime equals -22, u to the -2 times u, and u is 2x. So if I rewrite this, -22, I'm bringing that u minus 2 down to the bottom, and times 2x. And so I'm going to rewrite this one more time, is -44 x over u squared, and u is x squared plus 12. I feel like I just did something wrong. What did I do wrong? Oh, no, that's right. So that's the first derivative. Did everybody okay with that? Right? I multiply these two together, and I got -44. This u minus 2 goes to the bottom to u squared. I plug u back into it, and this is what I get for the first derivative. All right. I'm going to erase everything except that first derivative. So when you don't have an x on top, use the chain rule for a problem like this. Bring it to the top like I did, and then take the derivative. You know, and if you want to use the chain, well, yeah, you have to use the chain rule on this because we're busy on inside there. I mean, the derivative of the inside is more than just 1. It's 2x. All right, so everybody okay with that? So I'm going to erase this. So if there's not an x on top, bring that bottom up to the top with a negative power, and then use the chain rule. So we did that actually 3 times today. So this is my first derivative, negative 44x over x squared plus 12 to the 2 power. So that's the first derivative. Now we have to find the second derivative. And it might be hard to find the second derivative that they have. I'm going to try it. There's lots of room for error for me when I'm using this board because I don't get to follow it. But look at the difference between this and the first function. We have an x on top. We have an x on top and we have an x on the bottom. You can't use the, I would be a little worried about using the chain rule here because I can't bring it to, well, you could actually bring it to the top. Let's put it that way. You could actually bring this to the top. I'm going to erase this, but you could actually, that's times x squared plus 12 to the negative 2. You could actually bring it to the top and use the product rule. Do you see? You can actually, those two are multiplied together, use the product rule. Normally, I don't do that. I do it the way the book normally does a problem like this. And they use the quotient rule. This is F and this is G. If we have X's on the top and bottom, that's where we do the quotient rule. So if F equals negative 44x, why isn't my pen working? F prime is just negative 44. If G equals x squared plus 12 squared, I'm going to use the chain rule. I'm not finding G prime yet. G is the same thing as, this is the same thing as u to the second power, where u equals x squared plus 12 and u prime equals 2x. So the derivative of G, do you see we found F, we found the derivative of F, we found G, and now we're finding the derivative of G. The derivative of G is, bring the 2 in front, subtract 1, and then u prime. So G prime equals 2 times u, u is x squared plus 12, times u prime, which is 2x. These two can combine. G prime equals 4x times x squared plus 12. So we found all 3. Now we're going to use the quotient rule. And somebody help me with the quotient rule. I always forget which one goes first. F, G prime, or is it G prime F?
It's G and then F prime.
Minus G prime F, or F G prime, either way. All divided by G squared. Okay, so so I'm just going to fill in the blanks. Oh, Lord, I ran. Let me put the quotient rule up here so everybody sees it. G F prime minus F G prime all over G squared. Okay, so we're going to use the quotient rule. So first thing we do is plug G into here. G is right here. X squared plus 12 squared. Then we have G. Now we do F prime. F prime is negative 44. Minus F, which is negative 44x, times G prime, Oh, Lord, G prime is 4, negative 4x, x squared plus 12. All right, I think I have everything I need there. I'm going to erase some of this stuff now. I think we have it right. This is G f prime minus f 4. Oh, that's not, this is not right. There's no negative in front of that. I'm glad I didn't erase it yet. I think that's it. Yes, this looks like it. So I'm going to erase all this other stuff. Let me erase all this other stuff. I didn't want to erase G. So this is the top. Once again, it's, I'm going to rewrite it, negative 44 times x squared plus 12 squared. And a minus changes to a plus. And 4 times 44 is 170. Oh, wait, I'm just going to leave the 44. Oh, Lord. Yeah, 44 times 4 is 176 x squared. If we multiply these two together, we get a positive and this negative sign. We get a positive 176 x squared times x squared plus 12.
Mr. Trout,
Yes.
could we have done the factoring first? Because that's how I figured out this problem.
You pulled the negative 44 out.
Yes, and then I was left with an x minus 4x, I think.
Yeah, we could do that.
Because I think my first time around, I think I multiplied like the 44 and the 4, and it threw me out first.
Yeah, no, you can, but that's okay.
Okay.
Yeah, but I'm going to actually, let me do that now. So I'm only working on the top, everybody. Don't forget, we still have to put G squared. We have to square this and put it on the bottom. So now, like he said, I'm going to factor out. Normally, when you have a negative number in front of something, I'm going to factor out a negative 44. Not only am I going to factor out a negative 44, I'm factoring out a negative 44 and an x squared plus 12. So if you look, I'm going to divide this by negative 44 x squared plus 12, and I'm going to divide this by a negative 44 x squared plus 12. So that I'm going to divide both of those by that amount. Watch what happens. This cancels, and I'm just left with 1x squared plus 12 on the first spot. You see there was an x squared plus 12 here, and it canceled out with one of these. Then 176 divided by a negative 44, once again, is just a negative 4. I think, right? Negative 4 x squared. I don't know. That's why I didn't want to do this. I had to have it spread all the whole board. Negative 40, 176 is a negative 4 x squared. And that's it. We factored this out. This turns into a negative 4. And then we have an x squared, and we factored this out. And all of this is over the g squared. This is g x squared plus 12 squared, and then when you square that, it turns into a 4. You see, power of 2 times the power of 2 is the power of 4. One of these cancel out. Something still doesn't seem right. One of these cancel out. Do you see an x squared plus 12 cancels out with one of these? We have 4 on the bottom. Now on the bottom, we only have 3 because one canceled out with the top. We had 2 and 2, which is 4. So now we only have 3. And then a negative 44 is there. So this negative 44 is in front. For some reason, let me see the.
Did you factor out the 4 from the bracketed x squared plus 12 minus 4x squared?
See, that's why I don't know. Anyway, let me erase it and show what the answer that they get. Let me see. First derivative. So this is let me see. It definitely looks like there's something wrong in here. There's some. Oh no, we're okay. I think we're okay. 1x squared minus 4x squared is 12 minus 3x squared, correct?
Yes.
Okay. So we're okay. And I can factor out a 4 here. So and I'm gonna do it on top. I apologize. I have negative 44, and then I'm gonna factor out a 4 here. When I factor out a 4, I left with 3. I'm not factoring out a 4. I'm factoring out 3. So I'm left with a 4. 12 divided by 3 is 4, and 3 divided by 3 is x squared. So this is my top. So negative 44 times 3 is a negative 132, 4 minus x squared. So that's my top. Unfortunately, this is what the answer looks like in the book. Same thing I got, negative 132, 4 minus x squared, all over x squared plus 12 to the third. It's definitely, that's what I said, I hate doing these on one piece of paper. Even I get confused. I can imagine what you guys are going through. But I mean, like he said, you could have factored out the 44 first and then the 3 after, but this is the answer. If you look at the answer in that problem, this is the answer for the second derivative. So the second derivative, if you notice, when you have an x on top and an x on the bottom, use the quotient rule. And if you don't have that x on top, then use that chain rule. You know, bring the bottom to the top and use the chain rule. But I did get, I mean, for you to follow this, you would have to follow along, hit stop on the video, go a little bit further, hit stop. But we did end up with this answer. We did end up with the correct answer, even though it's so messy, and I apologize. That's why I like to use one huge board for this. But I did do the problem. Is that okay?
Thank you, because I had a really hard time. I figured it out, but I just wanted to hear I wanted to hear your voice and the way you explain things. Right. Because I'm so used to that. Because after this, I think it's just pretty straightforward. Yeah. With regards to to finding the change in the increasing and the decreasing in the function. Right.
Yeah. What else did this? Oh, this talks about concavity and everything. Determine the open intervals in which the graph is concave up and concave down. Well, let me write down. The second derivative. So let me talk. Yeah. Well, I know it's straightforward to you, but I do want to talk. Let me just, because I haven't talked about a concavity yet. So let's look at that. So when we talk about, I didn't even know this was a concavity problem. I was just worried about making sure everybody could do the first derivative and the second derivative. But this problem says discuss the concavity. So in order to do concavity, you have to have the second derivative. So we found the second derivative to be this. So this problem is never ending. We found the second derivative to be this. Okay, and so we need intervals. We need intervals, just like the first derivative, to finding if it's an increasing or decreasing slope. If you remember, we also use the second derivative to find intervals. and we set the second derivative equal to 0. When I find the second derivative equal to 0, can somebody tell me what the x values represent? What's another name for the x values I find? I have to solve for x, but what are the x values called?
Are they the critical points?
No, critical numbers is when the first derivative equals 0. So, and that's what I wanted to make sure everybody understands. These are critical numbers, but we're finding when the second derivative equals 0. They're not
Points of
called
inflection.
critical. They're inflection points, exactly. When the second derivative equals 0, they're called inflection points. And remember, inflection points are where concavity changes. That's why we go on both sides of the inflection points and find test points for those, and it'll tell us, oh, concavity is upper, concavity down. So inflection points when the second derivative equals 0. So that's what we're going to do. By the way, if I multiply both sides by the bottom, 0 times the bottom is still 0. So I get negative 132, 4 minus x squared equals 0. If I divide by negative 132, I get 4 minus x squared equals 0. So this is a pretty easy set equal to 0. Take the 4 to the other side, or take the x squared to the other side by adding x squared, and then square root both sides, and x equals plus or minus 2. These are our inflection points. So that it's important that you understand first derivative equals 0. Those x values are called critical numbers. Second derivative equals 0. Those points are called inflection points. Okay. All right, so if I look at the number line again, here is negative 2. Here is positive 2. I always like to put 0 in there, except 0 has nothing to do with the intervals here. So our first interval is from negative infinity to negative 2. Our second interval is from negative 2 to 2. Do you see? This is the second interval. That's why I hate putting 0 in there. People think 0 is part of it. But these are the inflection points. So the interval is here, here, and here. And the last interval is from 2 to infinity. So we're going to do test points in all three of these. I'm going to do a test point of negative 3. I'm going to do a test point of 0. And I'm going to do a test point of 3. And we need to find out, when we do these test points, we want to find out the second derivative. Is it positive or negative? So I'm going to plug negative 3 into the second derivative. Plug into f prime prime. So if I plug negative 3 into here, negative 3 squared is 9. 4 minus 9 is a negative 5. Negative 3, yeah, is a negative. Negative times a negative on top is a negative. Once again, I don't care what the numbers equal. I know the top's negative. If I plug in negative 3 down here, I get a positive number, positive. So this ends up being a negative number. And if you remember, when the first derivative, it says it's not negative. If I put a negative 3 in there, did I do something? Wait, if I put a negative 3 in there, I get a positive. It says the second derivative is positive on here. Did we write it down right? Negative 132, 4 minus x squared plus 12 to the third.
I think the numerator inside the parentheses is a negative, and a negative times a negative is a positive, divided by positive equals a positive.
Positive, positive. Oh, what did I say? Yeah, inside it, look, this is 4 minus x squared. 4 minus a negative 3 squared. Oh, that does. Negative 3 squared is 9. Oh, 4 minus 9 is a negative. Negative times a negative is a you're right. Oh boy. I don't know what I was thinking, but you're right. It does. It ends up being a positive. And if you get a positive test point, this interval, positive test point, this interval is concave up from whatever theorem that told us, right? If you get a positive second derivative test point, it's concave up. Now, if I put 0 in all these, I get a negative divided by a positive, I get a negative number. So this interval, we're concave down. And then when I put a 3 in there, just like the last 3, we ended up being a negative 3. We ended up with a positive, so it's concave up. So it's concave up in 2 spots. Those are concave up. Uh-oh, what did I just do again? I don't know what happened. Let me stop sharing and go back. For some reason, it goes away for some reason. That's not what I wanted. I wanted the whiteboard, and I think oh, it's still there. Good. So I have no idea what I was going to say now. This interval is concave down, and this interval is the, oh, that's what happens. I keep on hitting it. It's not maximized. There it is. Let me get rid of this and stretch this out. Is that it? There we go. Okay. So, and then from here, we're concave up. Let's look at the original problem again. So we're concave up, concave down, and concave up. Let's put this original problem in our calculator and just look at it. This will be the last thing I think we're going to do today. We're not running out of time, but I want to go back to the original problem and just look at it on the calculator. So this is the original problem. Let's type this function into our calculator. The original function is 22 over x squared plus 12. That's the original function. So let's take a look at that. Y equals 22 divided by parentheses x squared plus 12. And when I graph it, I got to go back to my settings because I had my settings all messed up. Negative 10, 10. And I do want to change my y values a little bit so I can see it better. It's kind of really hard to see. There we go. That makes it a little bit better. So here's my graph. I mean, there's the function that let me get, sorry. Trying to get the focus to work. I wonder if it's because the light's on here. Okay, there's my function. If I look at the graph, and I changed my window, just to let you know, I changed my y values to -5, 5, so you can see the function a little bit better. I'm gonna break out. If you double click my window, I think you're able to see the calculator a little bit better. So if I hit graph, we look at the interval from -infinity to -2. -2 is right here. See that point? That's the not the critical, now I'm saying it. That's the inflection point. Do you see this graph is a curve? It's concave up. You know, it's a graph with the curve looking up. I don't know how you want to say it. Concave up. At -2, concavity changes. Now the curve is going down from -2 to 2. Our curve is concave down. Our curve is falling out. Everything's falling out of it. It's concave down. And then from 2 to infinity, this graph is now, it's a big curve, but it is curving this way. It's curving like this. That's concave up. So you can actually see that on the graph. The hard part here is you can't see on the graph, you can't see the actual, the inflection point. You have to take the second derivative and make it equal to 0 to actually see that -2 and 2 are the points where concavity changes from concave up to concave down and then concave up again. So those inflection points tell you exactly where the concavity is changing on your original graph. All right, that's all I pretty much had for the day. I just wanted to go over and show you a few little derivatives and things like that. I hoped it helped. I'm going to hit stop.